Thanks for the introduction, and it is my greatest honor to be here, and I'm excited to talk about my work. So food has been identified as one of the top 10, actually top 3 problems for the next 50 years. If you think food is basically plants and animals, you can find that it has been related with many of the problems on the list, like the energy, water, environment, disease, population. Even terrorism and war has some kind of relationship with food. So think about a terrorist put some toxins into your food system that could cause severe consequences. So indeed, our food system is very vulnerable. It can be intentionally or unintentionally contaminated by a lot of things. For example, microbe, the top one is bacteria, and virus, fungi, parasite. Chemicals, for example, pesticides, antibiotics, adulterants, toxins, allergens. Engineered nanomaterials is an emerging food contaminant. Now we use quite a bit about the nanotechnology, but those nanomaterials, they prove that they have some potential risk. So that could be potential harms to the human beings. So the early on detection of this contaminant in food is really critical to keep our food system safe. However, current golden methods for detection of these 3 contaminants are all different. For example, for microbe like bacteria, the golden method is a culturing method, but that is very time-consuming. For chemicals like pesticides, we use the GC-LC-MS, which is a golden method, but that is very complicated and also it's very expensive. And there's no golden method that has to be established to detect of engineered nanomaterial in food yet. So the key challenges to detect these 3 contaminants in food is food. Because food is so complicated, it has a lot of different chemical compositions, physical structures, a lot of varieties, so really brought in a lot of interference for your detections. And food is usually produced in large quantities, so which means you need to have rapid, high throughput method, so that you need to think about both the yes or no screening method and quantitative validation method. And also the government regulations has set various tolerance levels for each of the contaminants in each food matrix. So that really requires your method to have some kind of sensitivity and specificity. So as I said, so far they are using different methods to detect different kinds of food contaminants. My research goal is trying to explore one tool that can detect all kinds of food contaminants. That is surface-enhanced Raman spectroscopy. And Lauren has touched on some SIRS in her talk, so I just briefly talk about these techniques. So I think these SIRS combines the Raman spectroscopy and the nanotechnology. So the Raman scattering provides a fingerprint of your sample. So it doesn't matter if it is bacteria or pesticide or nanomaterials, they all have its own Raman fingerprint. So that's the base for one detection for all. But Raman scattering is pretty weak, so that you need to use some kind of enhancement. So that's the metallic nanostructure being involved in. So to use this technique, there are 2 key components. The first one is the nano structures. It could be as simple as just gold nanoparticles that you can synthesize easily or you purchase online. You can fabricate a lot of different types of the nanostructure. So I think that's a pretty hot area in many engineering and chemical departments. They're trying to fabricate lots of different fancy structures for source application. Another key component to utilize this technique is instrument. It could be as small as a handheld Raman spectrometer so that you can do on-site detection, or it is a benchtop you can either couple with a microscope or not. Or you can assemble different pieces together to make it have a lot of different functions. So because I'm from the Department of Food Science, I actually don't know how to make fancy nano substrate. I can only make some simple ones, and mostly I buy the gold or silver nanoparticles. And I don't know how to assemble instruments, so I will just buy those cheap instruments in my lab. So this is to I have right now in my lab. So really, my research focus is methodology development to see how we can use search to detect each of these 3 contaminants in food. So here are some examples. Pesticide. There are hundreds of pesticides. Each of them is supposed to have its own unique Raman fingerprint. So detecting pesticide in pure solution is pretty easy. How about the food? So we developed the swab-based method, the ligand capture-based method to detect in the liquid. In situ surface detection, and the more recent study is we utilize penetrative gold nanoparticle to detect internalized pesticide to in situ and real-time monitoring pesticide penetration inside of the vegetables. Bacteria is different than the small molecule. Bacteria cells is about 1 to 3 micrometer, so that's about the same size of our laser spot. So when you're scanning the bacteria through on your search substrate, you can hit on and off to produce those hot spots. So that's indication of the presence of the bacteria. And because each different species of the bacteria, like Listeria, Salmonella, E. coli, they are different, have different Raman patterns, so that you can simultaneously identify them. So to detect bacteria in food, you need to have a captures that can specifically capture the bacteria so that you can remove out the food interference. Another design is this kind of sandwich-based assay. You use a capture to pour out the bacteria on a surface, then use the gold nanoparticle as the imaging probe so that you can do both optical imaging and the chemical imaging. So I call it a dual sensing mechanism. Engineered nanoparticle is a new direction in my lab. So the idea of using search to detect engineered nanomaterials is actually inspired when I did the pesticide in situ detection on the spinach leaves. So when we put the gold nanoparticle as a control on the spinach leaves, we found that those gold nanoparticles themselves have signals, and the signal varies from spot to spot. So then we decided to use those signals as a base for nanoparticle detection, as well as to study nanoparticle interaction with the plant. Okay, so now that is the most exciting work of our labs. So we are the first ones that reverse the search application. So traditionally, we use nanoparticle to detect the target. Now we use a Raman indicator chemicals to detect the presence of the nanoparticle in your system. Because search is is very nanoparticle specific. So then if you have an enhanced signal that indicates that there's nanoparticle in your system. So the Raman indicator is the key. We have selected several good indicators and proved it's a variable. It works in some complex matrix. And the current work is I call the triple functional ligand. So not only these ligands, they have a functional group that can bind the nanoparticle. They have a functional group that is very search active, so that is good for signaling. And also it has a lipophilic tail so that we can extract them from the complex food matrix. So the big picture in my field, I think that's the same for all kinds of analytical chemistry, that people always ask for faster, more sensitive, more accurate, more economic, more convenient detection. So if there's a method that can detect all contaminants in food at one step, that would be awesome. So far it is impossible, I would say, but at least our lab makes the first steps that is one tool for detect all those contaminants. So last, I want to share with you some of my experience of how to be a successful analytical chemist in the application area. So I think for the technical development, it comes with a theory, then initial instrumentation to prove the theory, and then continue commercialize the instrument so that it could be a variable and we can develop a lot of different analytical methodology for the real application. So for me, I'm mostly in these end areas. So compared with the scientists at the upper levels, I would say it is extremely difficult for us to publish Nature science paper. I don't have any Nature science paper, but I think I'm trying to solving the real problem. And I really appreciate the award committee that can recognized the importance of the chemist in the application side, like food science. And some tips is to do a good scientist in the application area, you really need to understand the problem and needs, and you need to be creative and develop different methodology. And also you need to communication back to the instrument company to develop some kind of user-friendly applications. And also, I'm also very excited to see what kind of new technology that I can translate into the food science application. So lastly, I want to thank the funding agency, especially the USD NIFA, that support us $2 million directly to the source work and total $3 million, and other institutes and companies, and the current key collaborators and my students. And thank you very much for your attention.